Welcome back, math friends. This is section 3.7, day 2 for AP Calculus. Today we are going to be talking more about the derivatives of log functions in the first part of our notes. And then in the second part of our notes, we're going to learn a new skill called logarithmic differentiation. But first, we're just going to do some application problems where we're going to be applying what we know to finding an equation of a tangent line and talking about increasing, decreasing, and concavity. So I caution you here, recall that our first derivative f of x gives us information about where f of x is increasing or decreasing, and our second derivative f prime prime of x gives us information about where our function f of x is either concave up or concave down. And that is information way back from chapter 2 content, so we have to keep that fresh and keep bringing it back in examples once in a while. So if we look at example 1, we're given this function y equals ln of x divided by x. So part A wants us to find equations for the lines tangent to the curve at 1, 0 and e 1 over e. So finding two different tangent lines to the same curve at two different locations. Again, a problem we've done many times before. Part B, we want to know on what interval is this function decreasing. So for that, we're going to be using our first derivative. And for part C, we want to know on what interval is f of x concave up. So we know for that one, we're going to need our second derivative. Beginning with part A, and actually, I guess before we get to part A, we need to differentiate our function and find y prime. So first of all, I'm going to rewrite y as 1 over x times natural log x, just because then I can use the product rule, and my preference is product rule to quotient rule. That's just a personal preference. So then y prime, my first function is 1 over x, my second function is ln x. So first d second plus second d first. First, 1 over x. D second, the derivative of ln x is 1 over x. Plus second, which is ln x, d first. And the derivative of 1 over x, if I bring it upstairs, is going to be negative 1 times x to the negative 2, or negative 1 over x squared. Okay, so then if I simplify this, I've got y prime is equal to 1 over x squared plus negative ln x over x squared. So I could combine these two with the same denominator. So I've got y prime is equal to 1 minus natural log x divided by x squared. Okay, so there's my first derivative, which I'm going to be using for both part A and part B. Part A wants us to find the equations for the tangent lines to the curves at 1, 0 and at e 1 over e. So let's start with 1, 0. I have my point. My point is 1, 0. I need my slope. So my slope is going to be equal to y prime of 1, which is going to be equal to 1 minus natural log of 1 divided by 1 squared. And natural log of 1 is 0, so I get 1 minus 0 divided by 1, which gives me a slope of 1. So then my tangent line, if I use point slope form, is going to be y minus 0 equals 1 times x minus 1, which gives me y equals 1x minus 1. So there's the tangent line to the curve at 1, 0. They also want us to find the tangent line to the curve at e 1 over e. So I need to find my slope first when x is e. So what my slope is going to be y prime of e, which is going to be equal to 1 minus natural log of e over e squared. And natural log of e is 1, So I end up with 1 minus 1 over e squared, but 1 minus 1 is 0, and 0 divided by anything is 0. So this tells me that my slope is 0. So that's going to make my tangent line equation pretty easy. Y minus 1 over e is going to be equal to 0 times x minus e. But again, 0 times anything is 0, so when I solve for y, I get y is equal to 1 over e. So there's the equation of the tangent line at the point e, 1 over e. Part A is done. So now we're going to do part B, which is on what interval is f of x decreasing. So for part B, we'll start by saying f of x is decreasing when f prime of x, when its first derivative is below the x-axis, right? So when its first derivative is less than 0. So I take the equation for my y prime, which is 1 over x squared times 1 minus the natural log of x. I just separated the numerator from the denominator there. And I want to know, when is that less than 0? Well, if I were to multiply, if I wanted to get rid of that x squared in the denominator, and I were to multiply both sides of the equation by x squared, 0 times anything is still 0, right? So I am left with 1 minus the natural log of x is still less than 0. And if I solve for x, I'm going to be subtracting 1 from both sides. So negative ln x is less than negative 1. And now I want to divide both sides by negative 1. And oop, I am dividing an inequality by negative. Ding, ding, ding. I have to switch my sign. So this is going to be natural log of x is greater than positive 1. And then right now, the variable I'm trying to solve for is stuck inside of a log. So I need to change form, or basically I need to raise both sides to the base of e. So this would be e to the ln x power is greater than e to the first power. And so then on the left side, I get x is greater than e, which tells me that my function f of x is going to be decreasing when my x values are bigger than e. So the answer to part B is going to be f of x is decreasing on the interval e to infinity, right, where x is greater than e. Now we get to part C, which says f of x, on what interval is f of x concave up? So we know f of x is concave up when its second derivative, f prime prime of x, is greater than 0. So I start with my first derivative. My first derivative I already found, right? That's y prime is equal to 1 over x squared times 1 minus ln x. And again, I wrote it like this because then it's a product, and I can use the product rule again when I'm finding my second derivative. So that's going to be my first job, is to find my second derivative using the product rule. So y prime prime is going to be first d second plus second d first. So first, 1 over x squared, derivative of the second. The derivative of 1 is 0. The derivative of negative ln x is going to be negative 1 over x. Plus second, 1 minus natural log x, d first. So the derivative of 1 over x squared, bring that x squared upstairs, it becomes x to the negative 2. And so then we have negative 2x to the negative 3, or negative 2 over x cubed. Okay, now let's clean this up. So y prime prime is going to be equal to negative 1 over x cubed. And then if I distribute that negative 2 over x cubed to the 1 minus ln x, I'm going to get negative 2 over x cubed. That's times the 1. And then I'm going to get positive 2 ln x over x cubed when I multiply it times the negative ln x. And then negative 1 over x cubed minus 2 over x cubed, That's going to make negative 3 over x cubed, and I can combine everything over the same denominator. So my y prime prime is going to be negative 3 plus 2 ln x all over x cubed. So I have my second derivative. So now I need to know, where is my second derivative greater than 0, right? So where is negative 3 plus 2 ln x divided by x cubed greater than 0? I don't want to mix up that math. So now I'm going to think about it the same way that I thought about this before. If I want to get rid of that x cubed in the denominator, then I'm going to multiply both sides by x cubed. It's going to get rid of the x cubed on the left, but it's going to have no effect on the right because 0 times anything is still 0. So now I have negative 3 plus 2 natural log x is greater than 0. If I add 3 to both sides, I have 2 ln x is greater than 3. And if I divide by 2, I have ln x is greater than 3/2. And now if I want to solve for x, I raise both sides to the power of e. So e to the natural log x is greater than e to the 3/2 power. So I get x has to be greater than e to the 3/2 power. So to answer my question here, f of x is concave up on the interval e to the 3/2 comma infinity. Okay, that's a great problem. We get to do our tangent line problem once again, and then it also brings back increasing, decreasing with our first derivative and concavity with our second derivative. Example 2 asks us to find the domain of the function f and then differentiate the function. Okay, well, first of all, we've got two things going on here. We know that as far as domain is concerned, our denominator can never be 0, right? So we know that 1 minus natural log of x minus 1 cannot equal 0. But we also know that anything that's inside of a log, whether it be a natural log or another base, has to stay positive, right? Has to stay greater than 0. So we also know that x minus 1 has to be greater than 0. And again, this one is because we can't divide by 0. And this one is because values inside logs must be positive. So let's figure out what x is allowed to be based on these two, and then we'll be able to combine them together and come up with our domain. So for the first one, if I subtract 1 from both sides, I get negative natural log of x minus 1 cannot be negative 1. Dividing both sides by negative 1 just makes this natural log of x minus 1 cannot be positive 1. If I raise both sides to a base of e to the natural log of x minus 1 cannot equal e to the first. The e and the natural log cancel out, so I get x minus 1 cannot be e to the first. And if I add 1 to both sides, I find out that x cannot be e plus 1. Okay? Then over here, this one's easier. I add 1 to both sides and I find out x has to be, greater than 1. Right? So when I combine these two together, x cannot be equal to e plus 1, which is a number that is bigger than 1, and x has to be greater than 1. My combined domain so these two combined are my domain. So my domain is going to be from 1 up to the value of e plus 1, but not including that value. And then from e plus 1 up to positive infinity. Okay, so here's my domain. That was the first thing that they asked us to do, is find the domain of f. And now they want us to find the derivative of f, which is going to be a little bit more complicated. So here's my f of x, which is equal to x over 1 minus natural log of x minus 1. Okay, so this is definitely going to be quotient rule. All right, so f prime of x, low d high. So 1 minus natural log of x minus 1, there's my low. D high, derivative of x is 1. Minus high, there's x. D low, so the derivative of 1 minus ln of x minus 1. All right, well, the derivative of 1 is 0. The derivative of negative ln x minus 1 is going to be negative 1 over x minus 1 times the derivative of x minus 1, which is just 1. But that is chain rule, technically. And this is all over low, 1 minus natural log of x minus 1, quantity squared. All right, so I can simplify my numerator a little bit. The calculus is technically done, and the rest is just algebra. So 1 times that bracket of 1 minus natural log of x minus 1, that's going to be 1 minus natural log of x minus 1. And then over here, I've got the negative x times the negative 1, so that's going to make plus x over x minus 1. But then this is all over that 1 minus natural log of x minus 1, that family being squared. So I don't like complex fractions. The first term is being divided by the x minus 1, but the second term is not. So if I move that x minus 1 into the denominator with that family that's being squared, then I'm going to need to multiply all of this by x minus 1, and then I can put that down there in the bottom. Okay, so that's going to be my next move. So I'm going to have f prime, not prime. F prime of x is going to be equal to, I'm going to have this x minus 1 times 1 minus the natural log of x minus 1 plus x, that's my whole numerator. And this is all being divided by 1 minus natural log of x minus 1 squared times that x minus 1 that I brought down to the bottom. And then we could simplify further, because if I distribute that x minus 1 to the 1 and the negative ln of x plus 1, then I'm going to have like terms with the two x's that I would be able to combine together. So that's going to be my last step here. Okay, is I'm going to take, I am going to take this x minus 1 right here, and I'm going to distribute it to the 1, and I'm going to distribute it to the natural log term. So I'm going to get f prime of x is equal to 1 times x minus 1 is x minus 1. And then I've got the negative x minus 1 times, ln of x minus 1 plus x over 1 minus natural log of x minus 1 family squared times x minus 1. And then finally, I can combine this x and this x. Those are like terms. So my final answer, as simple as I'm going to go today anyway, is going to be x plus x is 2x. So 2x minus 1 minus x minus 1 ln x minus 1 over 1 minus ln x minus 1, that family squared times x minus 1. And that's where I'm going to stop. You could certainly take it further. You could FOIL out that family in the denominator. You could multiply the x minus 1 through. There is more simplifying you can do, but at some point you kind of have to stop and say, am I making things worse or am I making things better? And if I'm making things worse, maybe I should stop here, right? So this is where I'm going to stop with my derivative f prime of x. Now we're going to switch gears a little bit, and we're going to talk about logarithmic differentiation. And logarithmic differentiation is just another trick in our bag of tricks. It's another way to differentiate something. And if you look at this function, y equals 2x minus 1 to the 5th times x to the 4th minus 3 family to the 6th power, this is something that we would typically use the product rule on, which would require us to use the power rule and the chain rule within the product rule. So I'm going to show you another way to differentiate this using natural logarithms. And it's actually a very easy process. The first step is you take the natural logarithm of both sides of the equation, and then you use the laws of logarithms to simplify the right side of the equal sign. So let me show you what I mean. Step 1 here, we're going to write natural log y is equal to natural log of 2x minus 1 to the 5th times x to the 4th minus 3 to the 6th, okay? And then when we use our laws of logarithms on the right-hand side, remember, if two things are being multiplied together inside of a log, that can be expanded to the addition of two separate logs. So I still have ln y is equal to, but now over here I'm going to have ln of 2x minus 1 to the 5th plus ln of x to the 4th minus 3 to the 6th. And then the next step is those exponents on those families can go in front of the log, right? That's using the power rule of logs. So now we have ln y is equal to 5 natural log 2x minus 1 plus 6 natural log x to the 4th minus 3. And then at this point, we haven't done technically any calculus yet, right? At this point, we're going to do step 2, which is we are going to differentiate implicitly with respect to x. So now I am going to do dy dx of both sides of the equal sign. So step 2, dy dx of natural log y is going to be equal to dy dx of 5 ln 2x minus 1 plus 6 ln x to the 4th minus 3. All right, so the derivative of natural log y is going to be 1 over y, but don't forget your chain rule. Y is a function of x, so 1 over y, y prime. And then over here, we just have natural log functions. So remember, derivative of a natural log, the coefficient comes along for the ride. So the 5 here and the 6 here are just going to be part of your derivatives, but it's going to be 1 over the stuff times the derivative of the stuff. So 5 over 2x minus 1, that's kind of 5 times 1 over the stuff, times the derivative of the stuff. Well, the derivative of 2x minus 1, that's just 2. Plus, over here, 6 times the natural log, so that's going to be 6 times 1 over the stuff, so x to the 4th plus 3, times the derivative of the stuff. Well, the derivative of x to the 4th plus 3 is just going to be 4x cubed. So now I have 1 over y times y prime is equal to 10 over 2x minus 1 plus 24x cubed over x to the 4th plus 3. And then, of course, the last step is I want to get rid of that 1 over y because I'm trying to find a derivative, so I want to know what does y prime equal. So my last step here, my step 3, is going to be, I'm just going to rewrite what I have here. I have 1 over y times y prime is equal to 10 over 2x minus 1 plus 24x cubed over x to the 4th plus 3. So if I want to undo that 1 over y, right, then I need to multiply both sides of the equation by y, because y will cancel the 1 over y. So my y prime is going to be equal to 10 over 2x minus 1 plus 24x cubed over x to the 4th plus 3. That times the value of y, which was 2x minus 1 to the 5th times x to the 4th minus 3 to the 6th. And there is the y prime using logarithmic differentiation. Example 4 is another opportunity for us to use logarithmic differentiation to find the derivative of the function. So we're going to do the same thing that we did in the previous problem. We're going to start by writing both sides, by taking the natural log of both sides. So natural log of y is equal to natural log of the square root of x e to the x squared times x squared plus 1 to the 10th power. Ooh, that's a doozy. All right, and again, I'm going to use the laws of logarithms to simplify this. So this is going to be natural log y is equal to, now all that stuff is being multiplied together, so I can split it apart into addition of individual logs. So this will be natural log of square root of x plus natural log of e to the x squared plus natural log of x squared plus 1 to the 10th power. And I can do a little bit of simplifying yet before I start my derivative. So ln y, now remember the square root of x is x to the 1/2 power. So I'm actually going to bring that 1/2 in front of the log. So 1/2 ln x is the same as the square root of x. Natural log of e to the x squared, the natural log and the e just cancel each other out. So this second term is actually just x squared. And then in my third term, I'm going to bring that 10 in front of my natural log, and it's going to be 10 ln of x squared plus 1. All right, so that's step 1. Now step 2, I'm ready to take the derivative of both sides, the dy dx step. So step 2, I'm going to do dy dx of natural log y, and I'm going to do dy dx of my 3 terms over here, 1/2 ln x plus x squared plus 10 natural log x squared plus 1. We know that dy dx of ln y is going to be 1 over y times y prime. And derivative of y with respect to x of 1/2 ln x is just going to be 1 over 2. That 1 over 2 is the 1/2, and then the derivative of ln x is just 1 over x. So I end up with 1 over 2x. Plus the derivative of x squared is 2x. And plus, we've got our 10, right? And then the derivative of natural log of something is 1 over the stuff. So x squared plus 1 times the derivative of that, and the derivative of x squared plus 1 is 2x. So we end up with 1 over y times y prime is equal to 1 over 2x plus 2x plus 10 times 2x would be 20x over x squared plus 1. And then our step 3 is where we multiply both sides of the equation by our y, right? So our step 3 here, our y prime is going to be equal to our 1 over 2x plus our 2x plus our 20x divided by x squared plus 1, all of that times y. So our final answer is going to be y prime is equal to 1 over 2x plus 2x plus 20x over x squared plus 1. That whole thing times our y, which was square root of x e to the x squared times x squared plus 1 to the 10th power. Sorry, I ran out of room there. X squared plus 1 to the 10th power. To finish up our notes here, we kind of have a little bit of a summary of different functions that we've been working on finding the derivatives of that contain exponents. So you need to kind of distinguish carefully between when you can use the power rule and when you cannot. So remember, the power rule is for when your base is a variable and your exponent is a constant, right? Whereas your rule for differentiating exponential functions is when your base is a number and your exponent is a variable. So in number 1, derivative with respect to x of a to the b power would be 0, first of all, because it would be like the derivative of 2 to the 5th. Well, 2 to the 5th is 32. 32 is a number. Derivative of a number is 0, right? The second one, derivative with respect to x of some function f of x to the b power. So again, this would be like power rule, right? F of x is our function like our x, and then b is our exponent. You'd bring the b down, you'd have your f of x, your exponent would become 1 less than b, whatever b was, and then if f of x is a function of x, you'd have to multiply by the derivative. That would be chain rule, right? But that's basically power rule with chain rule. Number 3 is going to be exponential differentiation, because your function is, your base is some number a, and your exponent is the function g of x. So again, this is going to be, the derivative is going to be the function itself, a to the g of x power, times natural log of a, right, times the natural log of the base, and then chain rule, if g of x isn't just x, if g of x is some function of x, then you'd have to multiply by the derivative of that exponent. So in the first one, we have derivative of a constant. In the second one, we have the power rule with the chain rule. In the third situation, we have an exponential function with the chain rule. Well, the fourth one is something new that we haven't seen before. So this is when we're trying to find the derivative of a function raised to a function. And so this is an example of where logarithmic differentiation comes in handy. So for our last example, we're going to differentiate a function raised to a function, y equals x to the cosine x power. So just like before, our first step is we're going to take the natural log of both sides of the equal sign. So we're going to have ln y is equal to ln of x to the cos x power. And then using the laws of logs, I can bring that cos x down in front of the natural log. Again, I haven't done any calculus yet. So then I have cos x times ln x, which is a product, right? So now step 2, now I can do dy dx or d dx of both sides of the equal sign, however you want to write that. So on the left side, the derivative of natural log y is going to be 1 over y times y prime, just like it has been in our previous examples. And then on the right-hand side, we have to do the product rule, right? Because we've got a product, cos x times ln x. So first d second plus second d first. Cos x is first. D second, derivative of natural log x is 1 over x plus second ln x. D first, derivative of cosine is negative sine x. And then I can simplify this. This is going to be 1 over y times y prime is equal to cos x over x minus sine x ln x. And then, of course, step 3 is if I want to get rid of that 1 over y, then I am going to multiply both sides of this equation by y, and the 1 over y will cancel the y, and I'll have my y prime, which is my derivative. So in step 3, my y prime is going to be equal to y times cos x over x minus sine x ln x, which y was x to the cos x power, right? So x to the cos x power times cos x over x minus sine x ln x. And there is my derivative using logarithmic differentiation. So again, anytime you have a function raised to a function, logarithmic differentiation is the way to go.